This is 7.2, right triangle trigonometry. So many of you guys have probably seen this in your past geometry classes. And if you've taken the Math 96, you kind of did a little bit of them. Some Math 96 people, instructors would actually do it. Some of them don't. But if you didn't, it's fine. We're going to do them here. So there are there are six trigonometric functions that we will be using a lot in this class, and we call them sine, cosine, tangent, cosecant, secant, and cotangent. So the first thing that you kind of have to look at is we have this right triangle, and remember a right angle has a 90-degree angle. So this guy right here is 90 degrees. All right. Remember also that if we look at all of the sum of the angles, so if I take theta and 90 in this, the measure of a triangle equals 180 degrees. That means if I take the sum of every angle, they should give me 180 degrees. Okay, now when we think about the trig functions, this is kind of how we're defining them. We're kind of relating the lengths of the triangle with the angle. So here is my angle theta. Okay, so here's where theta is at. So the side that is opposite of theta is, we're going to call it the opposite side. The side that is right next to theta, we're going to call it adjacent. And the longest side is what we're going to call the hypotenuse. So remember that the hypotenuse is just the longest side of a right triangle. Okay? So, and we kind of have seen this before. Remember that when we talk about hypotenuse, we have a right triangle and you have A, B, and C, you can relate all of this by the Pythagorean Theorem. A squared plus B squared equals C squared. So this is what we call the Pythagorean Theorem. Okay, so this theorem is really important because it's really useful in engineering. Okay, so Pythagorean Theorem, okay. So here's how we define all of them. So the sine is just equal to the opposite over the hypotenuse. Okay, so you take the opposite side and the hypotenuse. The cosine is the adjacent over the hypotenuse. And then the tangent is the opposite over the adjacent. Okay, now that's just basically how we kind of abbreviated all of this, guys. So think about it like in algebra, how we had like the natural log of x. So when we don't just write ln, that doesn't make any sense. It's ln of something. Or when we do logs, we have the log of 3 or something like that. Same thing here is the sine of what? Of theta. So the sine of the angle is the opposite of the hypotenuse. The cosine of the angle is the adjacent of the hypotenuse. So on and so forth. Then we have the secant, cosecant, and cotangent. So these guys are basically the reciprocal of them. So the reciprocal of cosine, right here, cosine theta, actually corresponds with secant. Okay, I know, super weird. Okay, so if I flip the hypotenuse and the adjacent, you get hypotenuse over adjacent. That's the secant. The opposite of sine is going to be cosecant. Okay, that's hypotenuse over opposite, so that's just flipped. And the opposite and the reciprocal of tangent is going to be cotangent. Okay, these guys really make sure that you know. You have to make sure that you really, really understand these guys because we're going to be doing them the entire semester. One really good way to kind of remember them is the acronym Sohcahtoa. Okay, Sohcahtoa. So basically what this means is that you have sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and then tangent is opposite over adjacent. Okay, so this is a really good way to kind of remember it. Now you have to be very careful because the opposite side can change. So it really depends on where theta is. So theta is right here. So obviously the opposite will be right there. However, if I have another triangle and now theta is up here, now the opposite is going to be right here. My adjacent is right there, and my hypotenuse never changes. My hypotenuse is always going to be across the 90-degree angle. So, but depending if I change theta, then my opposite has changed. Okay, so let's do this problem really quick. Okay, so let's say we have this triangle, and we want to find all 6 trigonometric functions. Okay, so let's start off with sine. So let's look for the sine of alpha. So notice this angle now is alpha. Sine of alpha. Remember that sine is going to be the opposite. Okay, so here's, remember this is opposite. Here is our adjacent. Here is our hypotenuse. It's going to be hypotenuse. Our sine is going to be the opposite over the hypotenuse. So in this case, my opposite is 8, and then my hypotenuse is going to be 17. So that's my answer. Okay, we're not doing anything else. Okay, we're not finding the angle. Okay, now let's look for the cosine of alpha. So don't just write cos, make sure that you write the cosine of what? Of alpha. The cosine is just the adjacent over the hypotenuse. So the adjacent in this case is the 15 divided by 17. That is my answer. Then we're looking for the tangent of alpha. So the tangent is going to be the opposite over the over the adjacent. So that's going to be 8 over 15. And now we can find the secant, cosecant, and cotangent. So like what I like to do is that the opposite of sine is going to be cosecant of alpha. That's going to be the opposite, okay? It's going to be the hypotenuse over the opposite. It's going to be 17 over 8. The secant is going to be the hypotenuse over the adjacent. So I always like to think about that's the opposite of the cosine. So just flipping it over. It's going to be 17 over 15. And then finally, the cotangent of alpha is going to be the adjacent over the opposite. That's going to be the 15 over 8. Okay. So it's not that difficult when you kind of already know what all of the sides are. It's pretty self-explanatory. Okay, so let's try this one. So find all 6 trigonometric functions given the following triangle. So notice that your A is now up here. Here's your angle A. Okay, so that means that this guy is going to be my opposite. This guy's going to be my adjacent. And this guy's going to be my hypotenuse. Uh-oh, we don't know what my hypotenuse is. So that means we have to think about how can I relate all 3 sides of a triangle together? Well, that's the Pythagorean theorem. That's a squared plus b squared equals c squared. We know that a squared is 4 squared plus 10 squared equals c squared. 4 squared is 16 plus 100 equals c squared. So this is going to be 116 equals c squared. We're going to take the square root. C is equal to the square root of 116. Okay, so let's go to my calculator. So I'm going to put square root of 116, and you'll see that this is 2 square root of 29. Okay, and notice that when we take a square root, you do add plus or minus. There is a plus or minus in here, but notice that we're going to get the positive side because the length of a triangle cannot be negative. Okay. All right, so now this is going to be 2 square root of 29. All right, so now what we're going to do is we're going to have all of our trigonometric functions. So we're going to start off with sine of A. Remember, sine of A is going to be the opposite over the hypotenuse. So that's going to be the 10 over 2 square root of 29. And reducing this is going to give me 5 over square root of 29. Okay. Then we have the cosine of A. The cosine of A is going to be the adjacent over the hypotenuse. That's going to be equal to 4 over 2 square root of 29, which is going to give me 2 over square root of 29. Okay. Now, typically, you would want to rationalize. I don't care about rationalizing, at least not at this point. Okay. Tangent of A is going to be the opposite over the adjacent. It's going to be 10 over 4, which is equal to 5 over 2. Okay. The reciprocal of sine is going to be cosecant. So I like doing cosecant. So that's just going to be the square root of 29 over 5. So that just is flipping the sign. The secant is going to be flipping the cosine. So square root of 29 over 2. And then the cotangent is going to be flipping the tangent, which is going to be 2/5. Okay, so once we kind of already know sine, cosine, and tangent, it's really easy to do the other ones. Okay, just as long as you remember Sohcahtoa. Okay, and the only thing to also remember is that sine does not go with secant, it goes with cosecant. And cosine goes with secant. I know it's really weird, okay? But tangent goes with tangent, so that's good, okay? All right, so now in this next section, we're going to talk about 45, 45, 90, and 39, 60, 90 triangles. Okay, so these type of triangles you do kind of want to keep in the back of your mind. So I guess this kind of just makes a little bit of sense. Like if you have a 45, 45, 90 triangle, one way to kind of think about it is that if these two angles or these two sides have to be exactly the same. Okay, so this side right here and this side are the same. So if I think of these two as being the same, well, this guy is just basically by the Pythagorean theorem. So in other words, if I have these two numbers, x and x, so let me just write it like this. So if I have x and x, what is going to be the other one? Well, we know that it's going to be x squared plus x squared equals whatever this guy, let's just say c squared. Well, this guy's just going to be 2x squared equals c squared. I'm going to divide this by 2, so I got x squared is equal to 1/2 c squared, okay? And then I'm going to take the square root to both sides. Oh, no. What am I doing? Have the 2 there. Okay. And then I'm going to take the square root to both sides, because we're solving for c squared. So you just have the square root of 2. The x squared is going to cancel out the square root, so you're left with x is equal to c. So that guy is just this guy. Okay, so basically the reason why this is a 45, 45, 90 is because you can see that if these guys are opposite of these angles, they should be exactly the same. If the measures are the same by similar triangles, we know that the length should also be the same. Okay. All right, now this one's a little bit more tricky to kind of think about. Imagine that you have this triangle, an equilateral triangle, which has all the same sides, so 60 degrees, 60 degrees, and 60 degrees. So if all of the degrees are the same, then the sides should also be the same. So let's just say, just for the sake of simplicity, that all of them were just 2. Okay, so you have 2 all around. Now what I'm going to do is I'm going to break up this triangle in half. Okay, so I'm going to break it in half. So I basically have one part of it. So when I divide it in half, this becomes a 90-degree angle. This becomes still 60 degrees. This is now 30 degrees because I broke it up in half. Okay, now this 2, the thing on the bottom, the length is now half of it, which is now 1. Okay, this guy still stays the same. Well, what is this guy now? Okay, this guy's not going to be 2. Okay, what exactly would it be? Well, by Pythagorean theorem, I can do it. So I know it's going to be 1 squared plus b squared equals 2 squared. So I have 1 plus b squared equals 4. B squared equals 3. So then b equals square root of 3. So this guy right here is going to be square root of 3. Okay, so that's where this square root of 3 came from. This 2's right there, and then you have a 1. Now, where are these x's coming from? Well, if I elongate it a little bit more. So if I, for example, if I wanted to make this into a 4, so let's say I had 60 and 30. If I wanted to make this twice as long, well, this is just not going to be a 4. Okay, if I want to make this guy twice as long, it's going to be 2 square root of 3. If I want to make this twice as long, it will be just a 2. So they're all basically just, if I were to elongate it, it'll just be whatever this guy is. So x is just telling you what the factor in which everything is just being multiplied. So if I want x to be 1, then this is the factor, the number right in front of it is the factor that's going to be stretched by, okay? One way that I like to remember this is that the 30 degrees is always right next to the square root of 3, okay? Because the other one's really easy to remember, okay? Now, these triangles are really, really useful because because we are kind of in an online setting. Typically, you do have to memorize these guys, but we are in an online setting, so just try your best to remember them, and this is going to be really useful when we try to look at the, how do you say it, at the unit circle, okay? So let's just do a couple of examples. So find the exact length of sine 30 degrees, tangent 60 degrees, and cosine of 45 degrees, okay? So we want to find the sine of 30 and the tangent of 30, okay? So let's start off with the 30, 60, 90 triangle. So we're looking at this type of triangle right here. So, so let me draw it out. So here's 90 degrees, here's 60 degrees, and here's 30 degrees. So we know this is 2, this is 1, and square root of 3. Oh, we forgot the x's. Okay, so you have all these x's. Okay, so all I'm just doing is I'm copying all of these guys. Okay, I'm just copying them. Okay, so the first thing that I want to do is find the sine of 30 degrees. So the sine of 30 degrees, so here's 30 degrees. Remember, that's going to be the opposite over the hypotenuse. So that's going to be this 1x over 2x. The x's are going to cancel out, so you're going to have 1/2. Okay? So now what we're going to look at is the tangent of 60 degrees. So the tangent of 60 degrees, so here's tangent. So now my opposite is going to be this guy, opposite over the adjacent. It's going to be x square root of 3 over 1x. The x's cancel out. I'm left with square root of 3. Okay. And now let's look at the cosine of 45 degrees. So the cosine of 45 degrees, well, let's draw a 45, 45, 90 triangle. So we know this is x, and x square root of 2. So the cosine of 45, it doesn't really matter which one we use. Okay. But remember that the cosine is always going to be the adjacent over the hypotenuse. So the cosine of 45 degrees is going to be the adjacent over the hypotenuse, which gives me 1 over square root of 2. Now, typically what you're going to see is a little rationalized form of this. So I'm going to rationalize it. The way that we rationalize is multiply by the square root on the bottom. So that's going to give me square root of 2 on the top, and then square root of 4, which is going to be square root of 2 over 2. Okay. So typically we like to do this because we don't like square roots on the denominator. And you're gonna see this a lot more. I don't really care when we do problems that look like this, like these. I don't really care. When we look them up in the unit circle, I am gonna rationalize them because it'll be a little nicer to look at. Okay. So this problem, let's go ahead and just do it really quickly. Or actually, let's just do it in the next video.